Have you ever wondered why, say, a tiny pebble just sinks right down in a pond, but then you see these massive, enormous ships floating?
Right. Seems counterintuitive, doesn't it?
Totally. Or, that feeling when you're trying to float in a lake versus the ocean. It just feels different.
Mm.
Well, you sent us your physics notes asking about exactly this sinking, floating, what's going on. So that's our deep dive today.
Yeah, we're looking at your Class 8 physics notes, Chapter 2, focusing on density and flotation. And while these might seem like basic ideas,
hmm
there's actually a lot of fascinating stuff under the surface, stuff that explains so much around us.
Absolutely. So our mission here is really to figure out how density works as the key, determining if something sinks or
And
floats.
we'll look at some real-world examples from the notes, too, to make it stick.
Great. So let's just jump in. Density, what is it exactly?
Okay, let's tackle that head on. Thinking about that ship in Pebble, density is basically how much stuff, mass, is packed into a certain space or volume. Your notes use a good example. Equal masses of iron and cotton. The iron's tiny, right? Small volume.
Yeah, compact.
But the cotton, huge fluffy pile, large volume. Same mass, but way different densities. The iron's much denser.
Okay, that clicks immediately. So how do we put a number on that? Is there a formula?
Yep, simple one. Density equals mass divided by volume.
E equals m over v.
Got it. V equals mv. Easy.
And units, how do we measure it?
Right, units.
Yeah.
The standard international one, the SI unit, is kilograms per cubic meter, kgm.
Okay.
You'll also see grams per cubic centimeter, GCM. That's the CGS unit, often used for smaller things.
And the notes mention a conversion.
Yeah, just so you know, 1 kilogmo is tiny compared to GCM. It's 1/1000th of a GCM.
Okay, good to know. Now, something that always tripped me up a bit, temperature. Your notes say it affects density. How?
Ah, yes, it's mostly about volume changing. See, when you heat most things up, their particles jiggle around more, spread out.
They expand.
Exactly, they expand, so the volume gets bigger. But the mass.
Stays the same.
Right. So same mass in a bigger volume means lower density.
Ah, density decreases.
And the opposite when you cool things. They usually contract, smaller volume, so density increases. Think like a hot air balloon. The air inside is hot.
Less dense.
Less dense than the cooler air outside, so it goes up.
Makes perfect sense with expansion and contraction. But the notes mention exceptions.
Water. Water is the classic weird one.
Right.
As it cools, it gets denser like you'd expect, but only down to 4 degrees Celsius.
Only to 4 degrees C.
Yep. Below that temperature, as it gets closer to freezing, it actually starts expanding again, becoming less dense.
That is weird.
It is.
Yeah.
Maximum density is right there at 4 degrees C, that 1,000 kilometer number. And that's why ice floats, because solid water, ice, is less dense than the cold liquid water around it. Super important for, well, life on Earth.
Definitely key. And another point from the notes. Changing the shape or size doesn't change the density of the actual material, right? Like gold is gold.
Exactly right. A gold earring, a gold bar of the material, gold has the same density. It's an intrinsic property.
Okay, so we know what density is. Now, how do we measure it? Your notes start with regular solids.
Right. Things like cubes, spheres, cylinders, things with easy shapes.
So what's the process there?
Yeah.
Seems straightforward.
It is pretty straightforward. First, find the mass. Use a beam balance, get your M.
Okay, mass M.
Then measure its dimensions, length, width, height for a cuboid, radius for a sphere. Use a ruler. Your notes have the formulas to calculate the volume, V, from those dimensions. Then just divide. Density, mass volume, D equals MV. Done.
Simple enough for a nice, neat cube.
Yeah.
But what about, like a lumpy rock? An irregular shape. You can't measure its sides easily.
Good question. That's where we use liquid displacement. It's a clever trick.
Displacement. Okay, how does that work?
Now take a measuring cylinder,
Yeah.
the tall tube with markings.
Yeah, got it.
Fill it with some liquid. Note the volume. Then carefully put your irregular object in. Make sure it's fully underwater.
Yeah.
Liquid level goes up.
Right.
The amount it goes up by is the volume of your object, because the object pushed aside or displaced exactly that much liquid.
Ah. So the volume of the displaced liquid equals the volume of the rock.
Precisely. Then you can calculate density just like before, now that you have the volume.
Very neat. And the notes also mention some specific tools for liquids, like those measuring cylinders and beakers.
Yeah, measuring cylinders are really for getting accurate volumes. Beakers are more for like holding stuff or approximate measures.
Okay.
And then there's the Eureka can, a bit more old school maybe.
Eureka can. What's that?
It's a can with a spout near the top. You fill it right up until water starts dripping from the spout.
Okay.
Then you put your object in. The water that overflows out the spout is collected, and that volume is exactly the object's volume. Another way to measure displacement.
Huh. Interesting. Okay, so we can find the volume of solids, regular or irregular. How do we find the density of a liquid? The notes give a couple of ways.
Right. The first way uses a standard beaker. Pretty simple. Weigh an empty dry beaker first. Get its mass, M1.
Okay.
Then use a measuring cylinder to measure out a very specific volume of your liquid, say 50 mmol. Pour that into the beaker. Weigh the beaker with the liquid in it. That's mass, M2.
Got it.
The mass of just the liquid is M2 minus M1. And you already know the volume you measured out. So density is mass, M2, M1, divided by volume.
Simple. Mass over volume again. And the second method, it mentions the density bottle. Sounds specialized.
It is. It's a small glass bottle designed for accuracy. It has a stopper with a tiny hole through it.
A hole in the stopper. Why?
When you fill the bottle completely and put the stopper in, any extra liquid gets squeezed out through that hole.
Yeah.
So it ensures the bottle always holds exactly the same, very precise volume. Your notes mention it used to be called a specific gravity bottle, too.
The specific gravity.
Yeah.
We'll probably get to that. So how do you use this bottle?
It involves a few weighings. First, weigh the empty, clean, dry bottle with its stopper. Let's call that M1.
Okay. M1 empty bottle.
Then, fill it completely with pure water. Put the stopper in, wipe off any water on the outside, weigh it again. That's M2.
Right.
Now, we know the density of water is very close to 1 gram per cubic centimeter. So the mass of the water inside, which is M2, M1, basically tells you the exact volume of the bottle in cubic centimeters.
Okay, clever. Using water as a reference to find the bottle's precise volume.
Exactly. Now, empty the bottle, dry it thoroughly, then fill it with the liquid you want to test. Stopper in, wipe it, weigh it again. That's M3.
M3, bottle with the test liquid.
The mass of just your test liquid is M3 minus M1, the empty bottle mass.
Okay.
And you already know the volume from the water step, which was essentially M2, M1. So the density of your liquid is its mass, M3, M1, divided by its volume, M2, M1.
That is precise. Okay, that makes sense. Now, the notes move to relative density. How's that different from just density?
Good question. Relative density, or RD, is fundamentally a comparison. It's a ratio.
A ratio of what?
It's the ratio of the density of your substance to the density of a reference substance. And usually that reference is water.
So it's like asking, how many times denser than water is this stuff?
Exactly that. Is it twice as dense, half as dense? That's what relative density tells you.
Okay.
And because it's a ratio density divided by density, the units cancel out.
Ah, so it doesn't have units.
Nope, it's just a number. Dimensionless. Your notes also say you can think of it as the mass of some volume of the substance compared to the mass of the exact same volume of water.
Right. Equal volumes comparison.
And that density bottle. You can use it to find relative density directly by comparing the mass of the liquid filling it, M3, M1, to the mass of water filling it, M2, M1.
Makes sense.
And here's a useful tip from the notes. Since water's density is about 1 GCM dsTO, the numerical value of a substance's density in GCMA is the same as its relative density.
Oh, handy. So if RD is 2.5, the density is 2.5 GCM.
Exactly.
And that term specific gravity that came up with the bottle.
Yeah, in practice, specific gravity is basically the same thing as relative density when water is the reference. They're often used interchangeably.
Okay, got it. Density measuring it relative density. Now let's get to the main event, really. Why things float or sink. This is probably what sparked the initial question.
Right, and the core rule, like your notes state, clearly comes back to density.
It's all about density.
Pretty much. If the object's density is less than the liquid's density, it floats. If the object's density is more than the liquid's density, it sinks.
Less dense floats, more dense sinks. Seems simple enough. But what's actually happening? What forces are involved?
Good point. There are two main forces acting on anything in a liquid. First, it's weight. Gravity pulling it down. That's the sinking force.
Okay, weight pulls down.
Second, there's an upward force from the liquid itself. We call it the buoyant force, or upthrust. It pushes up.
Buoyant force. Pushing up. So it's like a battle between weight down and buoyancy up.
Exactly. A tug of war. Your notes lay out the three outcomes. 1. If the weight, WA, is bigger than the buoyant force, FB, WFB, the object sinks. Downward force wins.
Makes sense.
2. If the weight equals the buoyant force, W equals FB, the object floats. Forces are balanced. It might be fully submerged if densities are equal, or partly if the object is less dense.
Balanced forces means floating. Okay.
3. If the weight is less than the buoyant force, WFB, well, the upward force is stronger, so it floats, and only part of it will be submerged until the forces balance out.
Right. So connecting back to density, a dense object weighs more for its size, so its weight is more likely to be greater than the buoyant force, sinks. And a less dense object weighs less for its size, so the buoyant force can balance or overcome its weight, floats.
You've got it. And that leads to the law of flotation. Really important principle.
Okay, the law of flotation.
It states, when something floats, the weight of the liquid, it pushes aside the displaced liquid by its submerged part, is exactly equal to the total weight of the floating object.
Wow. So the water pushed away weighs the same as the whole object?
Exactly. It's a perfect balance. And the notes add, the apparent weight of something floating is 0, because buoyancy cancels out gravity.
Feels weightless in the water, yeah.
And one more thing from the notes. If you put the same object in, say, very dense liquid versus less dense liquid, it floats higher with more of it sticking out in the denser liquid. Think floating in the Dead Sea versus a swimming pool.
Right. You're much more buoyant in salty water.
Yeah.
Okay, let's look at those real-world examples from the notes.
Yeah.
The classic, iron ship floats, iron nail sinks,
Why?
same material.
Perfect example of average density. The nail is solid iron, much denser than water, sinks.
Okay.
The ship, made of iron, yes, but it's mostly hollow, full of air.
Ah, the air inside.
That huge volume of air doesn't add much mass, so the overall density of the ship, the iron plus all that air averaged out over its total volume, is less than water's density.
So the ship as a whole is less dense than water.
Correct. It floats when the weight of water it displaces equals the ship's total weight.
That average density idea is crucial. Okay, what about swimming? Notes say it's easier in the sea.
Yep. Seawater has salt dissolved in it, makes it denser than fresh water.
Denser water.
Means you don't have to sink as far down to displace enough water to equal your weight. The buoyant force is stronger for the same submerged volume, basically, so you float higher, feels easier.
Explains that beach buoyancy. Okay, ice. We see it in drinks all the time. Notes mention a specific fraction submerged.
They do. Usually about 9/10 of the ice is below the water, 1/10 above.
9/10. Wow. Why that specific ratio?
It's just down to the densities. Ice density is about 0.9 GCN/m. Water density is about 1 GCM. That 0.9 to 1 ratio means 9/10 submerged.
Literally the tip of the iceberg. And speaking of icebergs, notes mention those too.
Right. Same idea, slightly different numbers. Ice is still 0.9 GCM, but seawater is denser than fresh, maybe 1.02 GCM or so.
So even more is hidden.
Yes. The vast bulk of an iceberg is underwater, which is why they're so dangerous for ships. You only see a small fraction.
Scary stuff. Okay, submarines. How do they control sinking and floating?
They use ballast tanks. Big tanks they can fill with water or empty.
Ballast tanks.
To dive, they let seawater flood into the tanks. That adds mass without changing the sub's overall size much.
Increases the average density.
Exactly. Average density becomes greater than seawater, so down they go.
And to come up.
They use compressed air to blow the water out of the tanks. Less mass, same volume.
Average density decreases.
Right. It becomes less dense than water, buoyant force takes over, and they rise.
Clever engineering.
Yeah.
Notes also mention whales and balloons.
Whales have something called a swim bladder. It's like an internal balloon.
Really?
Yeah. They can inflate it with air, which increases their volume without adding much mass, decreases their overall density, helps them rise. Deflate it, density increases, helps them dive.
Wow. Natural buoyancy control. And balloons.
Like helium balloons. Helium gas is way less dense than air. So the upward buoyant force from the surrounding heavier air pushing on the balloon is greater than the total weight of the balloon fabric plus the light helium inside. So up it goes.
It's all about density differences, whether it's air or water. Fascinating, from ships to whales.
Yeah.
It really is all about managing density. This has been really clarifying going through these notes.
It really has. We covered density itself, mass in a volume, how to measure it, this idea of relative density as a comparison, and then how all that dictates floating and sinking via weight and buoyancy, all from those foundational notes.
And it's amazing how these, fundamental physics rules explain stuff we see constantly. Ice floating, ship sailing.
Yeah.
Hopefully, listening along, you've had some of those aha moments connecting these ideas to the world.
Absolutely. And maybe a final thought to leave you with. We talked about changing density to sink or float, like submarines do. Could there be other ways? Could you manipulate, say, the buoyant force itself? Or use other forces entirely to achieve submersion or surfacing without just adding or removing mass?
Other ways besides changing density. Interesting to think about. Definitely something to ponder.